So welcome back, everybody. Again, like I said, we're going to begin the second half of the course. The stuff we're doing today is not rigorous. It's just a different look for some similar topics that we've done before. So we're going to do a little bit of review today on relations. Okay. So we're going to start with relation. Now, remember, what is a relation? A relation is nothing more than a set of ordered pairs, but it is not a random set of ordered pairs. Much like when we talked about a sequence is an infinite list, usually of numbers. It could actually be functions or symbols, but let's say it's an infinite list of numbers that has an underlying pattern that generates the list. If I just said, here is a random list of numbers and it goes forever, yes, technically that's a sequence, but if there's no way to generate the numbers, then you don't actually have an infinite list. You have a ... and you'd have to figure out the rest. So a sequence must have an underlying pattern for it to be a valid sequence. Well, a relation must have some sort of plan to generate the set of ordered pairs. Now, remember, the inputs come from the domain and the outputs come from the codomain. What you actually use is called, remember, what's the word for the actual things we use in the second number? The first is the domain. The second is the think baby algebra. Anybody? Starts with an R.
Range.
Yeah. People confuse codomain and range. Range is the amount of codomain you actually used. Oh, so if I said we're going to go from real numbers to real numbers, then my domain and codomain are the entire set of real numbers. Now, when I define my equation or my relation, what I actually use in that case, that's what the range comes from. And a lot of times we forget that. So the main thing is when we define our relation, okay, so let's say I'm going to define a relation this way. We will say X and Y are, and I'm going to be really, really loose, are related. We'll say it like that way. How about X over Y is an element of the positive integers. Okay, I'm going to define a relationship this way. Now, our input, okay, let's keep it really simple. Let's say our domain and codomain is the entire set of integers. I want to keep it really simple. So obviously X over Y therefore would be a rational number in general. So I want to take from the set of integers, every time I have a quotient that produces a positive integer, that's going to be, okay, in this situation. So let's define a set. Let's say set A is, how about the numbers -3, -1, 0, 2, 4, 6. And let's say set B is, how about -1, and I want to keep this really simple, 1 and 2 and 3. There we go. All right. So X will come from A, it will be a first set, and Y will come from B, that'll be our second set. So our ordered pairs are X comma Y, where X is from A and Y is from B. Now I have to generate, first of all, what are the things in my relation? So let's say, now we're going to formally define the relation. So we'd say it this way. X, and we often use capital R. I don't mind because R for relation, but we also use capital R for real numbers. And generally when we're using a capital R, we make it a script R if it's real numbers. So sometimes I'll use a different letter. So let's say we're using the letter T, just so we don't get confused. X is related to T, or X, T, Y. Okay, so T is my relation and X is related to TY if and only if X over Y is an element of the positive integers. Okay, this is how I'm defining this particular relation. So this is the formal definition. This was the, think of it as the verbal definition. So the first thing I need to do is actually create the potential ordered pairs that I might get. I'm not going to try to go through this and figure out which ones work. No, the first thing we're going to do is we're actually going to generate the Cartesian product. Now we've all done this many times. So the first thing is, what's the Cartesian product? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So this should be 24 ordered pairs. Yikes. Okay, I made this kind of big. So -3, -1, -3, 1, -3, 2, and -3, 3. And I'll do the same thing. -1, -1, -1, 1, -1, 2, and -1, 3. And I'm going to go dot, dot, dot. Okay, down to the end. And then the last one would be 6, -1, 6, 1. I'm never going to fit this on here otherwise. All right. So our Cartesian product would have 24 ordered pairs. Now, are all 24 ordered pairs in the relation T? So T technically is a set. The relation is X is related to T, or excuse me, X is related to Y through T if this statement is true. But then T is a relation, which means T is a set of ordered pairs. In this scenario, T is a finite set of ordered pairs because the ordered pairs in T can only come from the Cartesian product. If I didn't define A and B, and I said, well, we're going to use as our domain all positive integers and our range, our codomain all positive integers or all negative integers, well, then these would be infinite sets. That'd be a little bit too much. Hold on, where's my eraser here? Okay, so let me now squeeze. Okay, so now what is T? Remember, X over Y had to be a positive integer. So as I scan through my list, which ones will that work for? Well, -3, -1. How about -3, 1? Will that be in this? Will that be in T? Say,
No.
No, because I said positive integer. Oh, so they got to be the same sign, don't they? So -3, -1 will be one of them, but that's the only one that's going to involve -3. How about -1? Well, -1, 1. Or excuse me, -1, -1. All right, let's keep going. How about 0?
No, 0 is not positive.
Yeah, 0 over all of them will be an integer, but none of them will be positive integers. Aha. So I kind of tried to trick everybody. So then I've got 2, 1. I've got 2, 2. Okay. Then I've got 4, 1, and 4, 2. Then I've got 6, 1, 6, 2, 6, 3. So this is the relation T based on this definition. That's it. So once you have the definition, it's just, I hate to say plug and chug, but there's not a whole lot of thinking that has to take place. You just say, does this ordered pair satisfy this? But the key first step that a lot of people forget is I have to come up with the Cartesian product because this is where everything's coming from. I'm not taking it from, the entire universe of ordered pairs on the XY plane. No. No, so I actually have to define something. So in this case, when I give you the definition of the relation, then you say which ones satisfy this. And it's really, really simple. Now, what does it mean to be an inverse? So we remember what that means. This is sort of a minor thing, but we want to remember what that term means. If I said, now that does not mean reciprocal. I still have people in calculus who say, no, inverse means reciprocal. I'm confused by that. So the inverse of an exponent is a reciprocal. The inverse of a logarithm is a reciprocal. The inverse of trig functions are reciprocal. No, the inverse is the reciprocal of the infinitely many math operations that exist. Reciprocal and inverse are the same in one situation only, when you're multiplying. See, the inverse in an addition is the opposite sign, not the reciprocal. So this doesn't mean reciprocal ever unless I'm using exponents. And in other words, I'm multiplying. So T inverse is simply right, this. It's the exact same set where all of my elements are reversed, meaning my input and my output are reversed. Now, how do we remember if something is a function or not? Because there's always the confusion. An inverse can be a function, but it doesn't have to be a function. A relation can be a function. It does not have to be a function. A relation is simply a set of ordered pairs. And there's three ways I can think of ordered pairs. I can actually give you the list if the list is finite. But if the list is not finite, then giving something in an equation form is really, really nice. So I might give you the equation of a line. I might give you the equation of a parabola. I might give you the equation of a circle. Okay, all of those would generate infinitely many ordered pairs, but you'd know exactly how to find all of them. And the third way a relation can be expressed is actually graphically. If I give you the picture, then you can say, okay, I can glean the ordered pairs from the picture. So the way we determined, think baby algebra students, the way we determined if something was a function, there were three ways. Starting with the picture, you'd say, well, does it pass a vertical line test? That's the visual. That was the easiest one. But that means I had to start with the picture. And the picture might be the actual most difficult part of the process. Secondly, if I give you an equation, can I solve for y explicitly? So if we think of a circle, no, because y would be a plus or minus. That's not an explicit definition. So I'd have to be able to say y equals, and then all the x stuff on the other side, no plus or minuses, just one possibility. And the third way is if I give you a set of ordered pairs, -3 gets mapped to -1. -1 gets mapped to -1. Does this violate function? No, it does not. But over here, 2 gets mapped to 1 and 2 gets mapped to 2. Does this violate function? Yes, it does, because it means one input produced multiple outputs. That's how you violate function. Remember, it's if two different inputs give the same output, that's okay. That just means I'm not one-to-one. But that doesn't violate function, and we often get that one backwards. So the rule of thumb is if the original relation is a one-to-one function, then the inverse will also be a one-to-one function. One-to-one means it's a function, but every output came from a unique input as well. Okay, so that means if I drew all of the things for the first element, I drew all the things for the second element, and then I put the arrows, right? I would never have two different inputs going to the same output. I'd have every input going to a unique output and every output coming from a unique input. So that's just to remind us of those aspects. So this part of the process is supposed to be pretty simple. There's really nothing technical, nothing confusing. We're just reminding ourselves, but also using the notation. So then I can start asking questions about T. Or in this case here, is T a function? And you'd say, no, T is not a function because I found a couple of places, well, actually here, where one input produced multiple outputs. Okay. But if I had changed this definition of what I wanted my relation to be, the next relation might actually be a function. Now think of it this way. I'm going to stick with this A and B, and I'm just going to start messing around with this part here. Okay, I might say, now I want the difference to be a multiple of 3, or I want it to be the case where x times y is a positive integer, or, we can go on and on and on. There's an infinite number of variations I could perform, and some of those would lead to function, some of those would not. But in every case, okay, I would have started with this in every case, and then I'd say, which of these satisfies this? That's it. That's all there is to it. Again, nothing complicated. So now let's move on from this, because now the big ticket item of the day . All right, and we've used this term before, the next thing we're going to do, but we haven't gone into any detail or depth, I don't think. And that's what's called an equivalence relation. We started by reviewing what's a relation. Now we want to talk about something very specific called an equivalence relation. Now, an equivalence relation, there's 3, and they have very, very specific, very simple rules that they follow, but they don't change, they don't deviate. And the terms you're probably all familiar with. We have what's called reflexive, symmetric, and transitive. These are the three properties of an equivalence relation. And part of the reason we call it an equivalence relation is there are basically two different, they're not operations. Think of them more as comparisons, or like in the case of the T, X is related to Y by some specific definition. The equals and the congruence symbols are both equivalence relations because they satisfy all three of these. And the term equivalence relation comes from those, because if two quantities are identical, we say the quantities are equal. If I had two, let's say, shapes in 2 or 3 dimensions, and everything measurable about the shapes was identical, then we'd say the shapes are not equal. We'd say the shapes are congruent. So this identical nature of things, if things are identical, then we'd say they are equivalent. And that's, again, that's kind of a loose term. Numerically, we'd say they're equal. And in terms of shapes, we'd say they're congruent. So those are the two things that basically satisfy all three of these. Most things that you compare will not satisfy all three, but they might satisfy one or two. Now, when I say compare, I mean, I quite literally, I could say, I want my comparison today to be the comparison, my comparison is taller than, oops, that's my, I can't spell. That's my comparison. I want it. So I might have a list of students. And let's just keep it real simple. I have an alphabetized list of students. And if student A is taller than student B, then I've satisfied this relation. If student B is taller than student C, I've satisfied this relation. But if student E is not taller than student F, then they wouldn't satisfy the relation. That ordered pair would not be there. So is taller than is a very simple comparison. Think of it as it's just an inequality of heights. Okay, I could say is the same age as, that would be a comparison. Is prettier than, will live longer than. Okay, there's an infinite number of ways I could compare people in all these things. Makes more money than. Most of the time you'd think of these as being simple inequalities. But now here's how we test these things. So whatever my relation is, whatever I'm using as my comparison, and I'm going to keep it really, really vague. Let's just say I'm using S. So if X is related to Y, okay, then we'd say it satisfies the relationship. Okay, so it could be, I could be defining this as X is related to Y if X times Y is an even number. I could say X is related to Y if X over Y is rational. Any way I want to describe this, but S is my relation and X is related to Y, I will have a very specific definition. So here's how this works. Reflexive, whatever you're talking about is reflexive if X is related to itself. Something is to itself. The second one, if X is related to Y, then Y is related to X. Now, obviously, the is taller than relationship would fail. If X is taller than Y, then Y can't be taller than X, can it? Oh, that makes sense. And the transitive, if X is related to Y and Y is related to Z, then X is related to Z. Oh, so if X is taller than Y and Y is taller than Z, then it makes sense that X would be taller than Z. So the is taller than relation is definitely transitive. But is X taller than X? No, that doesn't make any sense. So that wouldn't work. So my is taller than relation is not reflexive. Clearly it's not symmetric, but it is definitely transitive. And most of the time, when you're thinking of something, it's going to be at least one of the three. Sometimes you get lucky, it's two of the three, and very rarely it could be three of the three. For example, what if my relation is X is related to Y if and only if X equals Y? Now think about that. X is related to Y if and only if X equals Y. This is my relation. Well, then is X related to X? Does X equal X? Yes, it does. If X equals Y, then Y equals X. Pretty sure that's also true. If X equals Y and Y equals Z, does X equal Z? Yep. So therefore, the equals relation satisfies all three. When a relation satisfies all three of these, then it is called an equivalence relation. Okay, if it doesn't satisfy all three, then it's not an equivalence relation. That's it. So that's why I said the equals and the congruence are ones that we know satisfy all three. Now, there can be other ones that do, but they're probably subsets of equals or subsets of congruence. And we're going to go through a few of these. This is not a difficult process, but it's understanding the logic and the terminology. You know, this is new for a lot of us. All right, so let's start with a really simple one. Okay. I'm going to start with a relation. All right. So we're going to go, S is going to map the real numbers onto the real numbers. So, some of you are familiar. This is sort of a linear algebra approach here. My input is coming from the real numbers. My output's coming from the real numbers. I'm not going to put any restrictions on this. All right. Now, here's the definition of S. X is related to Y, meaning X is coming from the domain and Y is coming from the codomain. It's always looked at it this way. I like using X and Y because most of us think of ordered pairs as X comma Y. I could use any symbols, but this just makes it easier for us to conceptualize. If and only if, let's keep it simple. If and only if 2 divides X minus Y. Now, what does that mean exactly? That means X minus Y is even. By the way, that doesn't mean that X or Y, neither X nor Y have to be integers. Oh, so for example, if X was root 2 plus 5 and Y was root 2 plus 3, then X minus Y would be 2. Okay, so X and Y are coming from the real numbers. It's just, if that result right there is a multiple of 2, then we'll say this is true. Now, more often than not, we'd really be using integers in this one, just so we don't have to think about it. But let's check this out. Let's see if this works. Okay, so let's start with reflexive. Question is X related to X? Well, X minus X is 0 and 2 divides 0 is a true statement, isn't it? Sometimes we get confused. 0 doesn't divide any number, but all numbers divide 0. Remember, because that means 0 is on top. In case we forgot what that means. So is it true? Yes. This relation is reflexive. How about symmetric? Okay. That's basically what we're saying. If this is true, then this is true. Well, let's see. What are we going to, therefore we're assuming, okay? So 2 divides X minus Y. What does that actually mean? That means there exists K in the set of integers such that what? X minus Y equals 2 times K. Okay. Don't, if, by the way, if you think something is false, if I don't think this is true and I can think of a counterexample, then by all means, your counterexample would prove it's false. For something to fail, a lot of times we get confused on this. For something to fail reflexive, symmetric, or transitive, it doesn't mean it has to fail it absolutely 100% of the time. It doesn't mean it's always false. It fails if it's not always true. It only has to be false once, and sometimes we forget that one. So this is what it means, okay? If this is true, then what is true? Okay, if X minus Y equals 2K, then what about Y minus X? Well, that would be negative 2K, which is 2 times negative K. And if K is an integer, negative K is an integer, and what do I got here? I've got Y minus K, excuse me, Y minus X is 2 times an integer. So this last statement here says that 2 divides Y minus X. Beautiful. Okay, so what have I got? If x minus y is a multiple of 2, then y minus x is a multiple of 2. That's kind of a no duh. I get that. But this is how we formally show it. Because if x minus y is a multiple of 2, then this statement is true. Then y minus x is still a multiple of 2. Okay, by factoring it out. So got that one checked off. Now let's go for transitive. So I got to erase this. Okay. This is what we're actually looking at, if that statement is true. So what do we know? So we're going to start by assuming both of these statements are true. Here you started by assuming this was true. You're not saying that S is related to, or X is related to Y for all things. No, 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 no. You're just saying if X is related to Y, then it's automatic that Y is related to X. That's what it means to be symmetric. It doesn't mean that X is related to Y for everything you can look at, not even close. So in this case, we're going to say that 2 divides X minus Y and 2 divides Y minus Z. That's what we're starting with. We want to conclude that 2 divides X minus Z. So from these two statements here, I can say there exists, how about, I don't know, let's say R and S integers such that X minus Y equals 2R and Y minus Z equals 2S. Okay. So if I say this, then can I put these two together somehow? Well, then if X minus Y is 2R and Y minus Z is 2S, then can I say that, so what's the last statement I want to do? X and Z. So I need to solve for X and Z. So what if I wrote this as X equals 2R plus Y, and here Z equals Y minus 2S. Okay, so if I've got these two statements right here, then what does that tell me about X minus Z? X minus Z therefore equals 2R plus Y minus Y minus 2S, which is 2R plus Y minus Y plus 2S. Oh, how nice. So that's 2 times R plus S. R plus S is an integer because R and S are integers, and we know that integer addition is closed. Oh, so let's say this equals 2t, where R plus S equals t is an integer because integer addition is closed. So what have we just proved? We just proved that 2 divides X minus Z. So my conclusion is 2 divides X minus Z, and therefore we have satisfied transitivity as well. Okay, a little bit of algebra involved, but this really wasn't that complicated. So the relation that I've defined here, two numbers are related if their difference is even. That's really what all that says. Their difference is a multiple of 2. Turns out that is an equivalence relation. Cool. You notice it also involved an equals somewhere in there. Now that's a simple one. So now I want to completely segue into a different area. I want to think geometry, because it turns out this stuff is extremely important in geometry. Because a lot of times when you're trying to write a geometric proof, what sort of things can you assume true? What kind of things can you get as results? So right now we're going to say that consider lines on the plane. Okay. In other words, I'm not thinking of lines in 3D. That changes things. We'll talk about that one also. So if it helps you think XY plane, I'm thinking of lines on the XY plane. Okay. My relation is going to be the parallel relation. All right. So we'll say it this way. For lines, I'll use L and M because that's kind of, I like to use that. So line L is related to line M. I'm going to use P is going to be my relation. if and only if L is parallel to M. That's what I'm calling it, a big P. Okay. L is related to M if and only if L is parallel to M. Now I'd like to know, and by the way, we're on the XY plane. We're in 2 dimensions. I would like to know if the parallel relation is reflexive, symmetric, transitive. So what I'd like you to do is on your own for just a couple minutes, I want you to think about it. I don't need a formal mathematical proof, okay? Because I want you to conceptualize this mostly. I want you to think about, is this going to be an equivalence relation? And if it's not, which ones are satisfied and which ones fail? So in other words, it either is an equivalence relation or it's not. So I want everyone to just take a moment. And what I'd like to do, I'm going to go to the gallery view for a moment here. And I just want you to just wave at me if you just one of them. If you have an answer to one of them, just let me know. Okay. I don't need anybody to answer all 3. Now, we're saying that 2 lines, L and M are lines. There's an infinite number of lines. What we're saying is L and M are not the same line. L and M are distinct lines. Otherwise, I would call them both the same thing. Okay, that's important. We realize that. I don't want that to be ambiguous in any way. So. All right. If you think you've got an answer to any one of these, just wave out, yell out. Again, I don't need a formal mathematical proof. I want this to be something that it's intuitive, that you say, yeah, I think this is, or no, I don't think this is because.
I think it's reflexive.
Okay, so what does reflexive mean? That would mean that L is parallel to L. What do you think? Is that true or false? This is a tricky one. Can a line be parallel to itself? By the way, do not think vectors, because this will totally confuse you. The definition of parallel vectors is not the same as the definition of parallel lines. Vectors are parallel if they're constant multiples of each other. Can L be parallel to itself?
Oh, yeah, parallel lines don't intersect. So
Therefore
it's not reflexive.
Does everybody agree with that? By the way, that's the first one that stumps everybody. By the way, I've been doing this for a million years, and everybody, oh God, I didn't even think of that. Yeah, a line can't be parallel to itself. By the way, just in case you forgot what parallel is, most people make the mistake of thinking of parallel in an equation form. Parallel does not indicate things are straight, by the way. See, I remind people, when you're driving on the freeway, and you're going through like the downtown S curve and you're driving on the freeway, all of your lanes are parallel. None of your lanes are straight. Parallel does not imply straight. Straight implies perhaps parallel. Parallel has 3 aspects. The first one, the most important one, Joseph just said, is non-intersecting. Same direction, equidistant. And my simplest example I use when I teach remedial algebra, I say, think of railroad tracks. Think of the railroad tracks. Do they stay equidistant? Well, they kind of need to, because if they don't, the train's not going to stay on the track. Are the 2 tracks going in the same direction? Yeah, I'm pretty sure. And most importantly, do the 2 tracks ever intersect? No, but are the tracks straight? No, but they bend together. So curves can be parallel as long as they meet those 3 criteria. Now, lines are the easiest thing to discuss when we're talking about parallel, but can't we also be talking about planes? Oh yeah, think of the walls in your house. Oh, okay, I have parallel walls. It's the first mistake people make, is they say parallel only applies to lines. No, parallel applies to 3-dimensional shapes, right? Non-intersecting, equidistant, same direction. And by the way, it doesn't have to be infinite. It can be finite. I can have line segments. I can have things. 2 pieces of paper can be parallel, right? But most of the time, geometrically, we're thinking infinite. So these are lines just to make it easier to conceptualize. Now, somebody I saw already answered the second question. You flashed it too fast. Anybody want to try this one? True or false? We should all agree on this one. Is this true or false? Remember, I said L and M have to be distinct lines. So L and M are not the same line.
True.
It's true.
Definitely true. If L and M are parallel, and sometimes it's easy, just like draw myself a picture. Okay, there's L, there's M. L is parallel. Oh yeah, that's like a no-brainer. The only way this could fail is if they were the same line, but that would not be distinct lines. Now the third one. Ooh, this one, believe it or not, this is not automatic. If L is parallel to M and M is parallel to N, and again, they are distinct lines, then L is parallel to N. That's either true absolutely always, or you can think of a counterexample. Remember, for it to be false, you do not have to prove it's false always. In the last problem that I did, if you guys remember, right, last problem I talked about multiples. And I said we were going from real numbers to real numbers. So if you're really thinking hard, you go, maybe I can come up with a situation where it fails. And that's actually how your brain should be working. Okay, I think it's either, here's how it works. It's either obviously true, or I can come up with a counterexample. Truth shouldn't be difficult to determine. Coming up with a counterexample might be tricky. Is this statement true? Remember, we're on the plane.
Professor, maybe you meant then L parallel to N, not M.
Did I say that?
In the end.
Thank you, Lexi. Thank you. N. Thank you. Yes. So
Yeah, that would be true, I think.
there's my L. Okay, there's my M. There's my N, and they are distinct lines. Yeah, that's going to be true. Parallel is a beautiful one because parallel satisfies symmetric and transitive, but it fails reflexive, which is, that's kind of odd that you'd fail reflexive. You'd think reflexive is the easiest one. Well, it depends what you're comparing. Now, everything's exactly the same. Oops, I'm going to change one thing. What is that symbol, everyone?
Perpendicular.
Perpendicular. All right, let's start from scratch. I love using geometry because it's easier to conceptualize than anything numerical, and there's no calculating. Okay, you never guess I was a high school geometry teacher for several years. You know, I love doing stuff like this. Yes, and they learned equivalence relations in high school geometry because it applied to so many things. And why did it apply? Because the congruence relation is so important. Probably the single most important result about this is the congruence relation is transitive. Oh, if I show shape A is congruent to shape B and I have shape B is congruent to C, I don't have to prove that A is congruent to C. That's transitivity. Another thing about transitivity, a lot of people don't realize, one of the most important algebraic techniques that all of us learned, even in baby algebra, is when I'm solving a system of equations is to use substitution, right? Where I solve for one variable and then I substitute it into the other equation. That is transitivity. That is the definition of transitivity of the equals relation. And so probably one of the single most important algebraic techniques any of you've performed is using substitution. And that comes directly from transitivity. That's why when you're writing an answer x equals 5 and somebody else writes 5 equal x, are they saying the same thing? Yes, they are, because that's the symmetric property of equality. You know, so we don't even realize how often we use this when we're doing math equations. Now, all right, folks, this should be a little bit easier. L perpendicular to L. What do you think?
No.
Pretty sure that one's going to fail. So nope. If L is perpendicular to M, then M is perpendicular to L. Now let's back up before we answer this one. What is the definition of, in terms of lines, it makes it easy, but in general, what is the definition of perpendicular? Ooh. And I used perpendicular rather than orthogonal simply because we're dealing with lines. Orthogonal is a more broad term that includes perpendicular.
Are you referring to perpendicular on a graph or like geometry?
What is
Because
the
there's
word?
two.
No, the word perpendicular has exactly one meaning. It has nothing
Oh,
to,
perpendicular to when two lines intersect and they form a right angle.
not lines, things.
Two
So
things, not lines.
Two things that not intersect, but how about meet? Because they could be finite.
Meet.
Meet at a, say it again, at a
Right angle.
at a right angle. That's the definition of perpendicular. The things don't have to be lines. I mean, look again, look at your walls. I sure hope your walls are perpendicular to your floor and ceiling, because if they aren't, your house is gonna, tip over at some point. Perpendicular just means things that meet at right angles. If they're infinite, we'd use the word intersect. Agreed? But I'm pretty sure that in your house, they're not intersecting, they're just meeting. So perpendicular has to do with very specifically right angle, and a definition of a right angle, of course, is the angle measures 90 degrees. We don't really need to go into that. So if L is at a right angle to M, does that automatically mean M is at a right angle to L? Yeah, I'm pretty sure that one's an easy one. But we have to make sure we remember exactly what does that mean. So this isn't vague and ambiguous, because the next L is perpendicular to M and M is perpendicular to N. Then L is perpendicular to N. We are on the plane. This is important. We're on the plane. Cynthia, I saw you shaking your head. On the plane. Okay, sorry. Okay, intuitive. Remember, it's either always true or you can find a situation where it's not. All right. Here's my L. Here's my M. Now I need a line that's perpendicular to N, or excuse, perpendicular. All right, here's my N. Beautiful. Oops. On the plane, L and N would have to be what? On the plane.
They're parallel.
They would have to be parallel on the plane. If I'm in 3D, no, all bets are off. In 3D, they can be perpendicular, but on the plane, they can't. Oh, so perpendicular is only symmetric. It fails transitivity. Now, let me go back to, hold on. Whoops. Give me one second. This always takes me forever to get back to everything. Pin myself. Okay, so this is a simple exercise in understanding, how we do and don't do. You found counterexamples. And by the way, is my picture an adequate counterexample for the geometry? Absolutely. Because remember, it's either always true or it's not always true. Not always true does not mean always false. The complement of a full glass of water isn't empty. The complement of full is something that's not full. So if something is always true or it's not always true, that just means you found one case where it failed. So the perpendicular relation is a beautiful one because it's actually pretty easy to conceptualize. Now, if I'm in 3D, this becomes much more challenging. You see, in 3D, I'm looking at my walls. Okay, now I have lines running along the ceiling that are clearly perpendicular to each other. Then I have a line running from the floor up to the ceiling. And so what I've got, or think of it as the X, Y, and Z axes in a sense, if I'm in 3D. And the X, Y, and Z axes are all mutually orthogonal or perpendicular. Okay, but in 3D, if the first line is perpendicular to the second and the second is perpendicular to the third, the first and the third can be perpendicular, but they don't have to be perpendicular. Right? Because you can still come up with a situation where they're not. So that one's a little bit trickier. That one's kind of fun. So the concept of reflexive symmetric transitive, okay, has to do with this. Now, this is actually a perfect segue because on the quiz, when people were doing the proofs, very particularly saying, what can I say next? You're going to write a geometry proof in general. Geometry I love because it's so clean. You have your given, and then you're maybe going to use definitions and axioms and postulates and maybe even theorems. So if this is true, then this is true. And if this is true, then this is true. So if step A is true, that implies B is true. If B is true, that implies C is true. If C is true, that implies D is true. But you can't start by saying A is true, therefore D is true. There's no connection there. You actually have to go through the stages because the first is implying the second is implying the third, and so on. And what you're doing there is, I've got this thing is congruent to this thing, and this thing is congruent to this thing. Implications are transitive. And we've been using that all along. We didn't realize it. If A implies B and B implies C, then A implies C is true. Yeah, implication is a transitive relation. Is implication symmetric? This is awesome. You never thought of this because we've been doing this all semester. Is implication symmetric? If A implies B, does B imply A? One person's taking a chance. Anybody? If A implies B, does B imply A?
Not always.
Good. How about it? Not necessarily, because A implies B is the conditional, B implies A is the converse. Is the converse always true? No.
It's not always true.
It's not always
But the
true.
converse can be true. It just cannot all. It just always is not.
Yeah.
Sometimes it's not true.
If a shape is a square, then it is a rectangle. If a shape is a rectangle, then it is a square. Not true. Can it be true? Yes. Is it always true? No. Remember, not always true does not mean always false. It just means not always true. So we know that implication does not necessarily go in reverse. That's called a biconditional when it does. Oh yeah, I remember that. Oh, that's an if and only if. Okay, cool. So things like implications, if A implies B and B implies C and C implies D, that's how I write a proof. And so on this one here, we had to do a series of steps. And most of you, by the way, did a really nice job. Every now and then I would email some of you and said, you skipped a step. So you might say, this statement is true. And then you did this big leap to the conclusion, and the conclusion is true, but you leaped through a few steps that were actually a series of implications that you can't go from point A to point D. You got to go A to B to C to D, because you're showing if this is true, then this is true, and this is true, then this is true. That's how you always write proofs, is you show the series of implications and the steps. This wouldn't be much different. Okay, think back to high school algebra, or in my case, my first calculus class. You know, I might have something like, I would have fun with something like this. I'd have a calculus class, and the instructor would have, you know, I don't know, x cubed plus 6 to the 4th power times x squared dx from 1 to 5, and the answer is, you know, 1,034,000, 63. Okay, I have no idea what the answer is. It's not important. I'd have an instructor, he'd write this and write this, and then I would be the one every time, and I'd raise my hand and I'd say, I don't see where you got the answer. He goes, oh, just do your substitution, change your variable, change your limits of integration, integrate the problem, plug it in. And I'd say, can you walk us through that? And absolutely 100% of the time, he got a different answer. Every single time he got a different answer. He would try to do problems in his head. Well, as we know in calculus, this is like 6 or 7 steps. You don't go from here to here. You show the algebra in between. Everybody knows that. If I have an algebraic equation, I don't write the answer. I whittle it down until I can get the answer, because otherwise no one would figure out where you got the answer from, even if the answer is correct. Well, this answer is not correct. I just made it up on the spot. But the point being, even if it was correct, nobody on planet Earth is going to see the connection here, because I left out all of the in-betweens. So when we're writing an algebraic, not a proof, just solving a problem. In a sense, it's like a proof. You're saying, if this is true, then this is true, then this is true, and then this is my final answer at the end. So we don't ever skip steps, because if you're skipping a step, then you are leaping on your implications and you're actually not using the transitivity. You're skipping those key steps, and maybe it's not true. I don't know. So one of the things that we have to make sure is always that the next step comes from the previous step, and so on. Now, I did a problem a little earlier where I was showing the transitivity on the one that's a multiple of 2. There are more than one way that you could successfully navigate that problem. Now let's do another one. Let's do a fairly simple one. All right. So my relation is this. I'm going to map. I'll use T again. T is going to map the integers to the integers. And again, this is linear algebra notation for those of you who've had Math 254, but it's actually universal. All that means is that's my domain, that's my codomain, that's my relation. That's it. I love this notation in baby algebra. Okay, we're gonna do functions in remedial algebra. Maybe our function is going to be f of x equals x squared. So in baby algebra, what would we say? F is mapping the real numbers to the real numbers is actually how you would be doing every single function in algebra and in pre-calculus and even in calculus. This is actually the formal way of stating the problem. That's my input, that's my output. F is my function, f of x. And it would make sense to call it f, not y. No. Careful with that, because y you're using as your second coordinate and x is your first coordinate, but that's your actual relation. Okay. So this is my thing here, and we'll say that, and by the way, once I write x, t, y, it's automatically implying that x is coming from the domain, y is coming from the codomain, and the ordered pairs are in the form x comma y. That actually does not have to be clearly spelled out. This is first, this is second. It's that easy. So the ordered pairs are x comma y automatically. And a lot of times we will overkill this and over explain it. It's not really necessary. Okay. If and only if, how about, oops. How about, let's keep it simple. 2x plus 3y equals 12. Huh. Now, what am I describing there? Anybody want to try this? What is that? Just blurt it out. Good. Not exactly. It's not a plane because if I only have x and y, what dimension am I in? I'm only in 2 dimensions, so therefore it's a line. Yes. By the way, could it be a plane? If I clearly stated I was in 3 dimensions, but then that would mean that my input here would have to be ordered pairs, and my output would be integers. So that's not quite the same. So I'm saying x and y have to be integers. Okay, keep it simple. And x is related to y if and only if this equation is true. Meaning, in simple English, x is related, every ordered pair in T is an ordered pair of integers that is on this line. That's all that means. Okay. Now, this one's going to be a little bit harder. So how do I attack this one? Well, first of all, I want everyone to think about this. I took something as simple as the equation of a line. All right. What do you think? Anybody? Is x related to x? So if x comma x is on that line, what am I saying here? I'm saying the ordered pair 12 comma fifths. Well, let's write this way: 12 comma fifths. 12 fifths comma. This is a point on this line on the xy plane, but my input and output had to come from the set of integers. Ooh,
Not true.
it's not true, because the only way this is true is if x was not an integer. So there is no integer where x is related to x. This fails reflexive. Yikes. And by the way, that was not a trivial thing. By me showing you this going, oh, wait a minute. I'm going from integer to integer. X is related to x. And by the way, this would have to be true for all inputs. The only input that it's ever true for is 12 fifths. So you could prove this, you could disprove this easily. Just make up a number. 1. 2 times 1 plus 3 times 1 is certainly not equal to 12. In fact, every integer you could possibly input would fail this. So this is one of those where it's actually always not true if I'm dealing with integers. Oh, so I failed reflexive badly. Let's write it this way. All right, so now, oops, I'll use a different color. It's hard to see otherwise. We have a tendency to think everything always works. Okay, If X is related to Y, then Y is related to X. Okay, so 2X plus 3Y is absolutely guaranteed to equal 12. What would that statement mean? What you think about this? This would mean that what? 2Y plus 3X equals 12. Oh, is that true? Is that true? Well, keep it simple. Think of an ordered pair. Think of an ordered pair that makes this true. I'll keep it simple. 6, 0. Over here, I'm switching the roles of X and Y. 6, 0 is most definitely on this line. But 0, 6, is that on this line? Well, actually, that was probably a lousy way of saying it. My input, if X is 6 and Y is 0. Now, if I put over here, X is 6 and Y is 0. That's sorry. X is 6 and Y is still 0. Is that true? No, that's not true. Most specifically, this is a different equation of a line than this one. So I'm going to fail symmetric. Now, transitive. Anybody got a gut feel? You think you're going to pass or fail transitive on this one? I'm showing you something that's actually a general conclusion in a moment. I just used the equation of a line. Do you think it'll be transitive? If I have an ordered pair that satisfies this one, okay, I'm telling you that 2X plus 3Y equals 12. And now we need to use a different letter of the alphabet. 2Y plus 3Z. And again, just think of this as being my input, and this is my input. So now the question earlier, you're saying, okay, is it 3D? Well, in a sense, yeah, kind of. Does that mean that 2X plus 3Z will equal 12? Well, think of an X and a Y, and then using the same Y with the Z, and now using the same X with that Z. Can you find a situation where it fails? Well, I'm giving you a hint. When I give you an equation in general, and I'm talking about an equation that would produce a graph, like keep it simple, XY plane, not 3D. If I give you an equation that produces a graph, is the equation itself going to satisfy an equivalence relation? Ooh. Can I just arbitrarily swap things in an equation form? The answer is probably not. So a better question is, are there equations that will satisfy equivalence relations? Now, the linear algebra folks, you know the answer to this. The answer is yes, but they're very, very specific types. Does anybody know the answer? What are the only types of equations that could satisfy equivalence relations? And not that they all would, but the only ones that can. Okay, no one's guessing. They're called linear transformations, which are the most important types of functions. And linear transformations all pass through the origin. See, this one didn't pass through the origin. So what if I made it pass through the origin? Might I have more luck? Maybe. See, if I had made that equal to 0, maybe things would happen. You know, maybe I can manipulate this differently, in other words. Now, all things that pass through the origin aren't necessarily linear transformations. All linear transformations pass through the origin. So that's one of the first and, you know, most important parts. So I'm going to stop here.